Okay, so this is going to be kind of the first video where we're really using the periodic table to discern information and figure out what's going on with an atom here. So this is kind of the very beginning of being able to apply this tool, make use of it. And so we're going to be drawing atoms, and we're going to be within what we call the Bohr model. So it'll be not the fried egg model. It's going to be a little bit more detail. So it's not just nucleus and electron cloud. We're going to have details on what's in the nucleus. We're going to have details about how the electron cloud is organized. And so we have maybe somewhat of an idea of what to do with the nucleus already. I kind of talked about that in the last video, how you can figure out protons and neutrons, but we're going to make sure that that's clear. And then we're going to talk about what we do with the electrons. And so if we start out, why not start at the beginning, right? So let's draw hydrogen. All right, and that's the only element name I'm going to write for the rest of this video. I told you, I'm a lazy chemist, all right? So, chemical symbol of H. And so if I look at my periodic table, like I said, mine's got a little bit more coloring on it, some notes. Hydrogen over here has one proton. And I'm going to draw the most common isotope. So if I don't specify, like, oh, it's hydrogen 2, 3, or 4, or 1, or anything like that, then I'm like, oh, okay, well, I just round this to the nearest one. So it's 1.01. I don't know if that focus very well, but there's a 1.01 there. So I'm going to say that's 1. And so that proton gives me a mass of 1. So that means there are 0 neutrons. Because if I had a neutron, which I abbreviate as N with a 0, protons are P with a plus. If I had a neutron, it would have to have a mass of 2. If I had 2 neutrons, it would be a mass of 3. So the proton gives me a mass of 1. That's what the periodic table tells me is the most common. And then I look and I go, okay, well, it's an element. So how many electrons are there? Well, same number as the protons. So 1 proton, 1 electron. All right. And so here's how I draw it. I have a proton in the nucleus, and I have an electron orbiting the nucleus. So there's my nucleus. Here's my electron cloud. It has 1 electron that orbits the nucleus. Now, I could do another isotope of hydrogen. What would that look like? So if I'm dealing with something like hydrogen 2, I already lied, I already wrote the element twice. But I'm not writing anything other than hydrogen. Alright. There's a 2 that goes in the top left, superscript 2. So that means that this has a mass of 2. Now hydrogen's still only going to have 1 proton. If it doesn't have 1 proton, it's not hydrogen. If it has 2, it's helium. If it's 3, it's lithium, so on and so forth. It's another element that we're dealing with. So 1 proton, that's what the name tells me. 1 proton. The mass tells me the number of neutrons. So if I go mass minus protons, so I go 2 minus 1, I have a 1 left over. That's my number of neutrons. So number of neutrons is mass minus number of protons. So keep that in mind. How do we know how many neutrons there are? Well, we get the mass from the periodic table, or it's given to us in the name, and then the number of protons is given to us by the element. So we subtract number of protons from the mass, we get number of neutrons. So in this case, this is hydrogen 2, which has a common name of deuterium. So it's a fancy isotope. It's used for shielding from radiation, stuff like that. Like in a nuclear power plant, the core is submerged in what's called heavy water. All the hydrogens in the water are deuterium, or a large fraction of those are, to help absorb radiation. All right, and so then it still only has 1 electron. It's just an elemental hydrogen. So 1 proton, 1 electron. There's no charge, no net charge. They zero out. Plus 1, minus 1 cancels out. And so what does this look like? Well, we get a proton, and I'm just going to go N for neutron, and then we have an electron. So again, our nucleus now has two pieces in it, a proton and a neutron, and we have an electron that orbits. So let's scale it up a little bit. So there's going to be some details with this periodic table that are important. So hydrogen just had one electron. So organization was easy. That electron just orbits the nucleus. But every one of these rows is a new electron shell. So the electron cloud has structure. And so there's a series of concentric shells that are each larger than the last. And so how do we know when to open up one of these new shells? Well, it's when we go across, once we fill a row and we open up a new row, a new shell opens up. So hydrogen and helium are in the first row. They fill the first shell. So hydrogen has one electron in the first shell, helium has the second, and that's all that fits in it. So oftentimes this is called the octet rule. First row is a little bit weird because it only has two electrons that fill it, but after that it goes 1, 2, 3, 4, 5, 6, 7, 8. So they call it the octet rule. And so we're going to do some examples of this. Don't worry. Like if you're having trouble seeing the small print here, no need to panic. So let's look at lithium. All right, so that's the first element in the second row. All right, so we go straight down from hydrogen. We're going to skip helium. I think you guys can figure it out. Feel free to practice it if you want. All right, so we're going to look at lithium. So lithium has an atomic number of 3. So that means there's 3 protons. And I didn't specify an isotope. I just said lithium. So the most common isotope is going to be 7. I just round 6.94 to the nearest 1. So that gets me a 7. And so if there's 3 protons, that means that there's going to be 4 neutrons. Okay. And it's going to have 3 electrons. All right. So those are all the pieces. So now we've got to put them together. All right. And so we're going to draw our nucleus, and I'm going to, like I said, there's shortcuts within shortcuts, right? I'm just going to go like this. I'm going to go, there's 3 protons and 4 neutrons. There's my nucleus right there. Okay? And then I'm going to have 3 electrons, and I'm going to go 1, 2. That fills the first shell. And then my third electron goes in the second shell. So lithium's in the second row, so it's going to have electrons in the second shell. So that's the trick. That's the last detail. Figuring out what's in the nucleus. That's what we talked about before. And now we know how to figure out total number of electrons, I think. You just match protons. When you deal with an element. This will change when we deal with like ions later. But as we fill it out, every time we go down a row, we have more and more shells. So let's look at, say, nitrogen. Okay, so we're going to stay in the second row here. And if you want, pause, take a crack at this, see how it works for you, and then come back to it, and I'm going to work through it here. All right, so I'll give you a second if you want to pause it. All right, so how many protons is nitrogen going to have? Should move this up so you can actually see. So it's going to be an atomic number of 7. 7 protons. And then we have a mass of 14.01. Would be the atomic weight would be 14.01. So that's going to round to 14, which means that we're also going to have 7 neutrons. All right, and then we just match number of electrons to number of protons, so 7 electrons. And I hope you use this little shortcut here, because when you get to something like, say, you know, calcium, you don't want to be drawing like 40 circles in your nucleus. That's too much. All right, and so actually I'll keep this here. I can't really fit that on there. All right, so we're going to draw the nucleus. We got 7 protons, 7 neutrons, and then we have 2 electrons in the first shell, right? And then it's full, just like before. There's 7 total, or you can count across. You go 1, 2, 3, 4, 5. There are 5 electrons in the second shell. So as we work our way across, as I said before, we're filling a shell. So nitrogen would have 5, oxygen 6, fluorine 7, neon It's noble gas. What makes a noble gas? It's filled that shell. Missing electrons in a shell is what drives chemistry. So if you have a full shell, neon doesn't really want to do chemistry. It's too noble for that. And so I'm going to draw them, 1, 2, 3, 4, 5. There we go. I'm not going to be super picky about where these are. Like this one, do you have it on the right, the left, up, down, and a diagonal? I don't care. As long as it's clearly not paired with the other two, you're good. Same deal here. As long as I see 5 on the outside, 2 on the inside, 7 protons, 7 neutrons, I'm happy. That's good. Thumbs up from me. So that's what I'm looking for. Alright, so let's crank this up a level. Alright. So actually, hold on. So every row opens up a new shell. As we go across that row, we're filling the shell. So let's jump to as complicated of an element as we can get. As soon as we hit transition metals, it all falls apart. So I can only do this trick up through calcium. And we'll back it up one. We'll do potassium. Okay? So we'll have potassium here. And so there's going to be a good number of shells in our electron cloud here, because we are going down to the 1, 2, 3, 4th row. So there should be 4 shells. Keep that in mind. Alright, so we're going to have 19 protons, because its atomic number is 19. And it's going to be 39 minus 19, so 20 neutrons. And I keep switching between capital N and lowercase n, doesn't matter. And we're going to have 19 electrons. But we also have to be aware of how those electrons are organized. So that's where we're going to really lean on the periodic table here. Okay, so first off, draw the nucleus, right? And I'm going to make this one very large because I need a lot of space for those shells. 19 protons, 20 neutrons. So there's my nucleus. Alright. Now, I have 19 electrons. I'm going to work my way through the periodic table here. So 1, 2, I fill the first row, which means I fill the first shell. Okay. 3, 4, 5, 6, 7, 8, 9, 10. So 10 total, but there's actually 1, 2, 3, 4, 5, 6, 7, 8 in this shell. I'm going to go electron, 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 electron. As long as there's 8 all orbiting together, I'm happy. So that gets me my first 10 electrons, and that fills the second shell with 8 more. Okay. Now we go down to sodium. Sodium's not potassium. Whoops. Sodium's not potassium. We're not done yet. So I'm going to have to put another 8 electrons in the 3rd row, or from the 3rd row into the 3rd shell. Alright. So that's what I'm doing here. 7 and 8. And then I just show that they are all orbiting together. And so what that is I've got all the electrons that account for everything up through argon. I've now filled the 3rd row. I'm not done though. I'm not at potassium yet. I need one more electron. And where's that electron going to go? In the 4th shell by itself. That is potassium. So quite a bit. And if we were to look, I could go one more. Guess what we do with calcium? Well, we adjust the nucleus and then we just one more electron on the outside. That gets us calcium. So, within this model, there's a couple things to talk about. So, this outermost shell, this outer electron shell, this is also known as the valence shell, which means that this is known as a valence electron because it's in the valence shell. So electrons that are in the outermost shell, the valence shell, are known as valence electrons. Now, all the electrons on the inside, we call those inner electrons. Like I said, we don't always get creative with the names. All right, so this is an inner electron, inner electron. These are all inner electrons. So there are 19 total electrons. Oops, keep having to pan around here. 19 total electrons. One of them is a valence electron, right there. The other 18 are called inner electrons. They're in the inner shell. Valence shell, valence electrons, inner electrons. That's how the system works. Now, what's so special about valence electrons? Well, when we're dealing with an atom, it just means they're the outermost electrons. But when we are talking about putting multiple atoms together, making compounds and molecules, things like that, valence electrons are the ones that are used in chemical reactions. So that's where the chemistry happens. The chemistry happens on the outside. You know, it's like an onion. You can't get to the inside without peeling around on the outside. And it's just the very outermost part. So I mentioned this earlier, but you know, having a full valence electron shell, having a full set of valence electrons like neon or argon. So I'm kind of, I said this before, but I use different language. But essentially, as we go across a row and we hit the end, neon has filled its valence shell. We do that again, we hit argon. It has filled its valence shell. When that valence shell is full, there is no need to do chemistry, because what's happening is, we'll talk about this more later. This is an early heads up. What's happening is either filling or emptying the shell drives chemistry. Those noble gases don't need to do that. So just be aware. This is where the chemistry happens. That's all you got to know for now. But I always like to sneak in kind of later details. All right, so the periodic table really ties into this, right? Now we can look at something like silicone and be like, oh, okay, well, it has 14 protons, atomic number of 14. Let's see, it has a mass of 28.09. Well, that means it's going to have 14 neutrons as well. And then those 14 electrons, so it's 14, 14, 14, nice symmetrical set of numbers. But those 14 electrons are going to be spread out among 1, 2, 3 shells. And there's going to be 1, 2 in the first shell, and then 1, 2, 3, 4, 5, 6, 7, 8 in the second shell, and then 1, 2, 3, 4 in the third shell. And we can draw that, you know, something like this. So you can do that for any element up to calcium. It all falls apart horribly as soon as these transition metals come into play. And that's for reasons we don't talk about in this class. If you want to know, you take general chemistry. All right, so feel free to practice that. Like I said, you can do any element on here. You can go through the ones I did. Just pause, like when I write the element, pause, take a shot at it, make sure it makes sense. And then if it's a specific isotope, you will be told here. So if I don't give a specific isotope, you just round the periodic table value to the nearest ones place and work off of that. All right, so you know, if you do have questions about this, let me know. But after this, we're going to talk about you know, a shortcut. We're going to simplify this even further. So we've expanded on the fried egg model. Like, this is everything in the atom. These valence electrons are what's used in chemistry. So we're going to talk about a shorthand notation that really only accounts for those, because that's all we really need as chemists. All right.